Strength of different materials. Steel, concrete and soil. Steel by strength is strength and compressive strength, concrete decide, and soil, shear strength. The presence of pore water will be a complex behavior to the soils. Mohr's Coulomb failure criterion in terms of total stresses. So tau F or tau at failure is equal to C plus sigma tan phi. This is a straight line equation. It's an equation for failure envelope. In this, phi is a friction angle and C is the cohesion intercept on shear axis, and this is drawn sigma versus tau, and tau F is maximum shear stress the soil can take without failure under normal stress of sigma. Mohr Coulomb failure criterion in terms of effective stresses. This is also drawn sigma effective and says tau. Tau F, tau at failure and shear stress at failure is equal to C dash plus sigma dash tan phi dash. The sigma phi is equal to sigma minus sigma total, that is minus u is the pore water pressure, sigma dashed is effective normal stress, and C dashed is the effective cohesion, and phi dashed is effective friction angle. Tau F is the maximum shear stress the soil can take without failure and a normal effective stress of the sigma dash. Mohr's Coulomb failure criterion. Shear strength consists of two components, cohesive and friction. In the effective or total, whatever it may. The frictional component is equal to sigma at failure into tan phi dash. Sigma dash at failure, sigma tan phi dash. And C dash is equal to cohesive component, which is an intercept to the shear strength axis. Mohr circle of stress. Take an element and effective stress sigma 1 dash is acting vertically and horizontal sigma 3 is acting, and there is a failure plane which makes theta angle to the base, and so tau is the shear stress and to that tangential to the failure plane, and sigma dash is normal to the failure plane. So tau is equal to sigma 1 dash minus sigma 3 dash by 2 and sine 2 theta. Sigma dash is equal to sigma 1 dash plus sigma 3 dash by 2 plus sigma 1 dash minus sigma 3 dash by 2 cos 2 theta. That leads to an equation which gives the circle. So the Mohr circle of stress equation is tau square plus sigma dash minus sigma 1 plus sigma 3 whole square by 2 is equal to sigma 1 dash minus sigma 3 dash by 2 whole square. That's equal to a circle. It can be drawn into a circle, and on the sigma, the starting point of circle is sigma 3 dash and the ending point is sigma 1 dashed, and the center point of the circle is sigma 1 dash plus sigma 3 dash by 2, and the radius of the circle is sigma 1 dash minus sigma 3 dash by 2. Mohr circles and failure envelope. Tau f is equal to c dash plus sigma dash tan phi dash, and there are two circles drawn, x and y. Y is stable because it is away from the tau x and it is below the failure envelope. X circle is touching a failure envelope, and it is a failure which is shown in the figure. Sigma increases and loading progresses and Mohr circle becomes larger. And finally, failure occurs when Mohr circle touches the envelope because the horizontal sigma 3 is not increasing, it is stable, and sigma sigma 1 increases slowly. So the diameter of the stress circle increases, and if it touches the whenever it touches the failure envelope, then the soil fails. Orientation of a failure plane. The failure envelope is like that, and a circle is the stress circle touches the just failure envelope, and the draw at sigma dash 3 to touch that failure point. Then the failure surface will come into picture. So it gives theta to the sigma, and PD is the pole with respect to plane. Therefore, this gives you 90 minus theta plus phi dashed is equal to theta. So theta is equal to 45 plus phi dashed by 2, or if it is a total stress, theta is equal to 45 plus pi by 2. Mohar-Columb failure criterion with Mohr circle of stresses. Failure envelope in terms of effective stresses is geometrically it is given. So C cot phi or C dashed cot phi dashed is given, and the center of the circle is sigma 1 dash plus sigma 3 dashed by 2 is also given. Then geometrically if you make it, sine of this is equal to sigma 1 minus sigma 1 dash minus sigma 3 dash by 2, and if you simplify this, so and making it possible, sigma 1 dash is equal to sigma 3 dash tan square 45 plus 5 by 2, and C 2C dash tan 45 plus 5 by 2. Determination of shear strength parameters of soil C and phi, or C dash or phi dash. Laboratory tests and specimens are taken from representative undisturbed soil sample or disturbed soil sample. And field tests are some vane shear tests and static penetration, standard penetration, so many things are there. But in laboratory, it is a direct shear test or a triaxial shear test. Other laboratory tests include direct simple shear test, torsional shear test, plane strain triaxial test, laboratory vane shear test, laboratory wall cone. So many are there, but we will take direct shear test and triaxial shear test. Laboratory test field conditions are representative of a soil sample, and if foundation or construction the load comes on it, then it acts as a sigma hc sigma vc plus delta sigma, because the construction slowly going on so that the loading increases. Simulating the field conditions in the laboratory, same way, and representative soil sample taken from the site. Step 1. Set the specimen in the apparatus and apply the initial stress condition. Step 2. Apply the corresponding field stress condition, means increment of stress. Direct shear test. Direct shear test is on a small box and test procedure. Porous plates are there, sheet of ball is there, and the vertical stress is there, and the pressure plate and all that. It's a proving ring which gives the shear force. So apply a vertical stress to the specimen and wait for consolidation, and lower the box in the subject to horizontal displacement at constant rate. So lower one will move and upper one will be stable, and like that, and so that you will give proving ring measurement of shear force, that divided by the area of the specimen gives the shear stress, and the normal stress P is there, divided by the area will give you the normal stress, and sigma is equal to normal stress and normal force divided by area of cross section sample, and tau is the shear stress, shear resistance developed at the sliding surface is equal to area of cross section of this sample. The cross sectional area of the sample changes with the horizontal displacement. So the direct shear stress is conducted on three types of samples, each time changing the normal stress P. So each normal stress you will get corresponding shear stress. All the three makes 3 points, and all the 3 points are plotted normal stress versus shear stress at failure. Then combine all these three, you will get a straight line, and the straight line gives you, it makes an angle with the y-axis, that is C, and the slope of that straight line is phi, that is friction. Advantage of direct shear test apparatus. Due to the smaller thickness of the sample, rapid drainage can be achieved. Can be used to determine interface strength parameters. Clay samples can be oriented along the plane of weakness of an identified failure plane. Disadvantages of the direct shear test also are there. Failure occurs along a predetermined failure plane. Area of the sliding surface changes as the test progresses. Non-uniform distribution of shear stress along the failure surface occurs. Triaxial shear stress. It's also a sample, failure plane is there, failure sample is there, soil sample and a failure plane. Natural shear failure plane occurs, and there is an impervious membrane on the top, and porous stones are kept, and the water is inside, and that gives the pressure, all round pressure of that, and cell pressure, and that is there, and back pressure. So many equipments can be there, and it's a gradual P is applied through piston. Types of triaxial test. It's the drainage valve if the open, a consolidated sample is tested, or if drainage valve is closed, then unconsolidated sample is there. And if the drainage loading is there, undrained loading is there, and this is the shear load under all round cell pressure. It is done. Then the step 2 is that delta sigma is equal to K. That is deviatoric stress. It is called as deviatory stress. So how to determine the strength parameters C and phi values? Mohr's envelope is drawn for the test for three all-round pressures, different all-round pressures, different shear stresses are come, and then draw the circle. You can draw a circle making the Mohr Coulomb failure envelope, and all the the failure envelope should touch all these three circles. Draw the failure envelope. Then once if it touches the shear stress axis, then that intercept is C, and the slope of that failure envelope which is drawn touching the three circles is phi. The vane shear stress. This is one of the most versatile and widely used device used for investigating untrained shear strength CU and sensitivity of the soft clays. This test is very simple and it should be done only for sea soils only, and H is the height of the vane, then D is the diameter of the vane, then the vanes are shown, and a torque is applied on the top. So rotation will takes place 6 degrees to 12 mm per minute, and test can be conducted at 0.5 meter vertical intervals. So the vane shear stress Cu is equal to the torque applied by pi into d square, that is the diameter of the vanes, and h is the height of the vane, and plus dq by 6, that is diameter of the vane.